All right. So in this case, we are going to consider this is a pre-2017 exam on our AC theory. So that is question number 2. So considering this typical exam, that is considered 2.1, we are given an impedance is connected in series with two impedances in parallel. One of these impedance, then we are given another one. This combination is then connected across a 140 alternating current supply. Okay, so let us just see our diagram. I think that will be the best way. Just consider your diagram here. So they many impedances that you're given. So there is an impedance, the first one. Remember, if you're adding like this, it means there's a resistor and an inductor. That is R plus JXL. So there's an inductor there. Also, there's a plus here, meaning to say there's an inductor. Where there's a minus, there is a capacitor. You can just indicate that, or you can just indicate your impedance just as a single resistor, as long as you understand what is it that you are representing on that part. All right. So let us consider to say the first one is just gonna write this one. There's an there is a resistor and an inductor there. But like I said, you can just consider as a single resistor as it is. All right. So that is the whole of this part is given, which is 8,5. So let's just call this Z1. So this is equal to 8,5 plus J 9,5. All right. So it is connected in series with the two impedances. There are two impedances in parallel. These two impedances, they are in what? In parallel. So meaning to say this connection that we are going to have, it is connected to a parallel combination where there are two impedances that we are given. All right. These impedances, we are given the first one, 10,5 plus, which is there is an inductor there, a resistor, and an inductor, but you can just write as Z, which is Z2. All right. So the whole of this part is our Z2, which is a combination. That is 10,5 plus J, 16,5. All right, so this is our impedance. Then another one, which is the one that is in series with, that is the 14 minus J7. So which is a capacitor. When remember your impedance, when there is a negative, that is minus XC, to say that there is a capacitor there. So you're just going to call this Z3, which is 14 minus J7 ohms. So this is the one that you're given. So that is the combination, which is everything that we are given here that we had before. This is this combination is then connected across the 140 alternating. So meaning to say, we are just going to take our combination to the alternating current. All right, so that is something like this. Just gonna consider, all right, this is just a sketch. Okay, so this is just a sketch that we are having here. All right, sorry for that. Just gonna consider this way. So that's we have got an alternating current there, an alternating voltage of 140. So the voltage is given as 140. We do not have the frequency, all right? So the frequency is not given. So this is what you're given, the whole of this part. That is what you have. That is the sketch. Let us consider this to say the question is to calculate 2.11, that is the total impedance, okay? So for the total impedance, it will be wise that we also do convert these in polar form so that for our calculations, we're not gonna have any challenges later on, because remember, once you're dealing with complex numbers, there are conditions where rectangular form is important. I explained about that even in our N4. There are conditions where it is also best to work with a polar form. So in that case, it will be best of nature that you do convert these at once. All right, so the first one is given as, that is 8,5 plus. So in polar form, remember, I'm going to have this shift to polar form. So you just press as it is 8,5. Then you separate this, that is shift, put this comma here. All right, then 9,5. So this will give us the answer in polar form. Remember, in polar form, you are supposed to have r angle of theta. So you're given your r there and also your theta. All right, that's our r in this case. Sorry for that. Need this one. Is 12, that's 12,748. If you round off to 3 decimal place, that will be 8 there. So you are changing or writing each and every part. So this will be Z1, so in polar form. So we have got this as 12,748. The angle that we are given, that is 48. If you have to consider here the theta, just move aside. It's 48, that will be changed. That will change 10 and that will be 418. So it's going to be 48,18 degrees. So this is what you're going to do even on Z2. Z2 is given as 10,5. So shift to polar form. That is 10,5. Then you're going to separate this. All right, that is, we need alpha, not alpha, but this shift here. Sorry for that. So you're going to need shift so that you access this comma. All right, so that's 16,5. Then we're going to have this in polar form. All right, so R there is 19,55. That will be 8 if you round off. So there our Z2 can be written as 19,558. Then the angle theta, which is 57,5288, which is going to be 29. So this is 57,529 degrees. All right, so I've got Z2, the same thing with your Z3 to polar form. So just have a tendency of doing this so that later on, you're not going to have a challenge whenever you're calculating your values. So that was going to give us our Z3, which is 15,6, and also the angle being negative 26,526, and so on and so on. So that is your polar form. So that was going to be 15,652. And the angle was negative 26,565. All right. So that is, we have got everything in polar form and also in rectangular form. We need the total impedance, remember, that is the condition of our question 2.11, the total impedance. So in order for you to have the total impedance, you are going to consider this Z1, which is in series to whatever that we have, but it is connected to a parallel combination. So meaning to say, to find ZT, you're going to consider Z1 plus the parallel combination, which is of Z2 and Z3. So you can calculate your parallel combination aside. The parallel combination, remember, product over sum. So we are going to consider Z2 times Z3 over the sum, Z2 plus Z3. And considering the product, I said this before, that a product, it is best for you to calculate a product in polar form. You're going to notice that from your complex numbers in N4. Then addition, it is best for you to do addition in rectangular form. So that's Z1, we're gonna, Z2 and Z3, we're gonna take them in polar form for a product. All right, so that is Z2 already in polar form. So that is the advantage of converting these already. You've got these ones in polar form. So anyways, even if you're not having these ones, you're going to be forced again to calculate these. So that is, you do not have a way, you have to calculate these values, all right? Then Z3, in polar form. So you consider Z3 in polar form, that is 15,652. The 652, then the angle, that is minus 26,565. All right, we also have the angle there. All right, then in rectangular form, you see that, for addition, you see that rectangular form is the best for you to have in addition, because you're just going to add your real terms, imaginary terms. So you're taking your Z2 and your Z3 as they are, but in rectangular form for addition, it's best that you do add in a rectangular form. So that's 10,5 plus J 16,5 plus Z3 in rectangular form, that is 14 minus J7. So this is it. In polar form, multiplying, remember, you're going to multiply your numbers together. So you multiply the numbers, then the angles you add. So you multiply 19,55, this to this value. That is to 3 decimal places. You're going to have 306,122. Then the angles you add in polar form. If you're multiplying, you add. If you're subtracting, it means you are dividing. Remember your mathematics N4, guys. So that was going to give us 30,964 degrees. Then if you add in rectangular form, remember the real terms together. So 10,5 was going to add to 14, which is 24,5. Then we've got J 16,5 minus J7, 16,5 minus 7, that's 9,5. And you have to convert this to polar form because you are to divide. And I talked about this conversion. So that means if you were to convert, you were going to obtain something of this nature. If you were to convert this using that conversion to polar form, that was going to give us 26,277. That's 277. Then the angle was going to give you 21,194. So I want you to convert that using the condition shift to polar form. Then you write everything as it is. So we are back to the division in polar form. I talked about this division. You divide the numbers together. So if you divide the numbers, that was going to give us 11,65. Then the angles you subtract. So these angles that you're given, this time you subtract. So that's 30,964 minus 21,194, which is going to give us 9,7702, 3 decimal places, just 977. So this is the impedance that we are having of the parallel combination from our product over sum, which is in polar form. The answer that you're obtaining is in polar form. You can also convert this to rectangular form. Remember, we do not, because we're going to add. Remember here we said ZT is going to be Z1 plus Z parallel, which is for the parallel. So meaning to say it is best, remember I said addition is best in what? A rectangular form. So you can even convert this to rectangular form. So this time we have to press the shift to rectangular form. That is shift, you press to rectangular form. Then as it is 11,65, then you separate this shift comma, that is 9,77. This will give us the answer that is in what? In rectangular form. So that is, we have got 11,481. So that is 11,481. Then we have to check the Y. Is it a negative or a positive? If it is a positive, that is positive J. The part of Y, remember, Z is equal to X plus or minus JY according to your calculator. So that will be 1,977. Okay, 977. So that is, we're going to have 1,977 ohms. So this is just another format, which is the rectangular format. So now we can calculate our total impedance, because we said the total impedance is Z1 plus Z2, because Z1 plus the Z parallel. Because this is now a single impedance. So these two will be in series. So you have to add now. So ZT was going to be from Z1 plus Z parallel. That's Z1 in rectangular form. That is, it is best addition in rectangular form, 8,5 plus J 9,5. So that's, we're going to have Z1, all right, plus Z2, or I mean, Z parallel. Already in rectangular form, we converted this. That's 11,481 plus J 1,977. So adding the real terms together, the imaginary terms together, that means we're going to add 8,5 to 11,481. And that was going to give us 19,981. Adding the imaginary this time, that is, we're going to have a plus 9,5 plus 1,977, which was going to be 11,477. All right, so this is our total impedance in rectangular form. We are obtaining this in rectangular form. I talked about this converting also to polar form. So shift polar form, you convert to polar form. This was going to be 23.042. Then the angle was going to be 29,874 degrees. So this is your polar form if you want to write in polar form. So in this case, you were not forced like to write this in rectangular or polar form. You can even just leave your answer like this, but just for future calculations, because you might need this where you are dividing and you have to convert. But in case that you do not need this, you can just leave your answer in rectangular form. So these are the stages that you're supposed to have made, considering that it's a parallel series parallel. So the parallel, you work it on its own, then you add to the series. All right. Then 2.12, it was to calculate the total current. Now that we have got the total impedance, we can calculate the total current, as we know that from our Ohm's law, current is taken to be voltage over resistance. So this time, we are going to consider it as the voltage over the impedance. So the total current in that case will be the total voltage over the total impedance. So since we have got a division, it will be best that we use the polar form. I talked about this. So V is 140. The angle is going to be at 0 if it is not given. Then remember, we calculated ZT and we even have this in polar form. So we are going to take our ZT in polar form, which is this one. So that is, we are going to divide. Division is best in polar form. I talked about this one. So meaning to say at the end, this we're going to divide, all right, to the ZT that we had, which was 23,042. Then the angle that we are given, it was 29,874. So this will give us the total current. And this value in polar form, if you divide, remember, polar form, divide the numbers separately, that will be 6,076. Then the angles you subtract. So that's 0 minus this value, that will be minus 29,874 degrees. All right, so that is our total current for the whole circuit. For the whole circuit that you're given, that is our total current. Then from this part, we are also given to calculate the power factor. All right, 2.13, the power factor. As we can see, our total current, it has got a negative, meaning to say the current is lagging the voltage, all right, by 29,876, because the voltage was taken at 0. Remember, the voltage was at 0 degrees. So it means the current is lagging directly by the angle that we are given, because the voltage, remember, it's at 0 degrees. So the current is lagging by this. So the power factor can be taken as a lagging power factor, knowing that power factor is equal to the cos of theta. That is the cosine of the angle theta, 29,874 degrees. That will be our power factor, 0,867. Having a current lagging to the voltage, that is a lagging power factor, a negative, meaning to say our power factor is lagging. So that was the question that we had. If you consider the first part of the question, this is 10 marks out of 20. So the second part again, it's another condition that you have to again just make a sketch. A coil with a resistance of 28 ohms and an inductance is connected in parallel with a circuit consisting, there's a capacitor. All right, so this is a coil. So the resistance and inductance here, they are part of the coil. All right, so it's something like this, it's an RL circuit. So this part is having the resistance 28 ohms and also the inductance of 0.07 henries, which is building up our coil. Like the whole of this part is the coil. This is connected in parallel with a circuit consisting of a capacitor. So where it is connected, it's a circuit consisting of a capacitor. So you can even have the capacitor on top. It's up to you. So the capacitor is 140 microfarad. So this is what you're given in series with a, all right, sorry for that. We still have something that is to consider on our capacitor there. So the capacitor is not just on its own. The capacitor that we have is in series with a 22 ohm resistor. So meaning to say we have got an RC circuit there. All right. So this is like the whole of the part that you're given. So the resistance being 22 ohms and the capacitance being 140 microfarad. So you're given the capacitance 140. Then the supply. So meaning say the whole of the combination that we are given is then later on connected to the supply. So meaning to say in this case, we just have the same voltage across of 250 at 50 hertz. All right. So this is an AC circuit that you're given having a voltage of 250 volts, then the frequency being 50 hertz. All right, so in this case, we just have something that is a little bit different from what we had in this case here. All right, just a little bit. There we are given the reactance is already calculated. Here they are giving us exactly the values of the capacitor. We have to calculate the reactances, the reactance of the capacitor, the reactance of the inductor. We have to calculate those ones. So what is the question? 2.21, calculate the following: the total supply current and the current in each branch. So we need the total supply and also the current in each branch. So considering across the coil, maybe this is your current one, across the RC circuit, maybe this is your I2. It's just going to consider the way that you want to have it, or you can just consider as I coil or whatever that you want, guys. You can even write this as I coil. It's up to you. But as you can see, in order for you to have this, we need the impedance, the total impedance to the total voltage, as we saw previously, that in order for us to have the total current, we needed the total impedance. So actually, it's just a follow-up of what you had before, only that they did not ask you to calculate the total impedance. But as you can see, you need the total impedance. So to find the total impedance, this is a parallel combination that we are seeing. So meaning to say our total impedance is the parallel impedance that we are having. So considering the Z coil, we can just consider this as Z1 or just Z coil. It's up to you. So I'm just going to consider Z1 and Z2. These two are in parallel. So meaning to say our ZT was going to be product over sum Z1, Z2 over the sum Z1 plus Z2, where our Z1 is that of the coil. Our Z1 is equal to Z coil. This is the impedance of the coil. So as we know, we are going to need this impedance, which is taken from R plus. This is in polar form. rectangular form. So meaning to say that was going to be R plus, it's an inductance, so that is plus XL. We are forced to calculate the XL and XC. All right, so let us just calculate our XL and XC aside here. So these are the stages that you'll be being forced to calculate all these. All right, so XL is equal to 2 pi FL. As we understand this, that is 2 pi times the frequency, 50 Hertz times the inductance. Remember, that's 0.07, meaning to say you're going to obtain your XL as 21.911 ohms. So having this, we can find Z1, which is equal to the Z coil. This is the impedance of the coil. So that is the resistance, 28 plus JXL. Our XL is 21.911. It is always best that you just do convert again to polar form. So to polar form, I talked about this conversion, guys. You're going to obtain 35.603. All right, then the angle was going to be 38.146 degrees. So this was going to be your Z1. Again, you're going to need Z2 from the RC circuit. So you're going to see that our Z2 in this case, because an RC circuit, it was going to be R minus JXC, meaning to say you need to calculate XC, which is the reactance of the capacitor. The reactance of the capacitor from 1 over 2 pi FC, that is going to be 1 over 2 pi times the frequency of 50. Then the capacitance, that is 140 times 10 to the exponent of -6 from the microfarad. So this gives us the value of XC, which was going to be 22.736 ohms. So having XC, that's you're going to have your Z2, which is the resistance across the RC circuit, that is 22, minus JXC, which is 22.736. That is 736 ohms. In rectangular form, again, convert to polar form using your calculator. You are going to obtain. So if you check, there was actually a mistake. If you consider your memo, I want you to see this, what you're going to have here, because there it is supposed to be to polar form. All right, so that is 22. Then you separate this with a minus 22.736 like this. This was going to give you 31.736. Take note, 31.637. Take note about this one. So it was actually a mistake there. 31.637, and it actually affects everything that you're going to have later on. And the angle, it was supposed to be minus 45.943 if you round off to 3 decimal places. So that's minus 45.943 degrees. All right. So this was your Z2, which is the impedance. This is the impedance that you are to consider in this case of the RC circuit, all right, in both rectangular and polar form. So remember we said to find ZT, we are going to need this product over sum concept. So meaning to say our ZT from product over sum, it is going to be the product, and I referred that product is best in polar form, sum it's best in rectangular form. So you're going to take Z1 of the polar form on the product. That's 35.603, the angle being 38.146 degrees. All right, that's our Z1 times Z2. Let's consider our Z2 in this case, the product in polar form. Again, take your Z2, that is 31.637. Then the angle was minus 45.943 degrees. All right, so this is it. You divide, what are you dividing to? Z1 plus Z2, the sum. which is best to have in rectangular form. So Z1 in rectangular form, that is 28 plus J 21,911 plus Z2 in rectangular form, our Z2 here in rectangular form, that's 22 minus J 22.736. So that is what you're going to have. So considering the polar form, remember your multiplication, multiply the numbers separately. That was going to give us 1,126,372. Then the angles, you add the part of the angles you're going to add. So if we add 35,146 to minus 45,943, you were going to obtain minus 7,797 degrees to 3 decimal places. Then you add, remember, a rectangular form, gonna add 28 to 22. That was going to give us a 50. So there we have got 50. Then you add the imaginary part. So that's 21 minus 22 because there's a negative there. So it's 21 minus 22.736. And that was going to give us a negative. That's negative J 0,745. So this is what you have. Division best to be done in polar form. So meaning to say this is just a repetition of the previous question if you check. So that is, let us divide 372, this one. We just need to convert the second part, which is the rectangular format to polar form. Remember your conversion. So you're going to get something like 50,006 to 3 decimal places. Then the angle, it was going to give you minus 0,854 degrees. All right. So in this case, you are going to divide. Remember, division, divide the numbers separately. That was going to give us 22,525. Then the angles, what are you going to do? You subtract. So that's minus 7,797 minus 0, that's 0,854. So you subtract, but there is minus already, so it's going to be a plus. So that was going to give us minus 6,943 degrees, which is measured in ohms. So the question was to calculate the total impedance. So with the total impedance, maybe we are going to need it, but in division, we know that division is best to have it in what? In polar form. So to have the total supply current, it means you're just going to divide with this impedance that we have calculated in polar form. All right, so these are the stages, guys. Calculate this, you move on. From that, you calculate another part, just like that. So everything sums up to what you're given there. So now the total current from the total impedance, voltage over the total impedance. Remember, the supply voltage is 250, so that's 250 at angle of 0 degrees. That is the voltage that we are given as our supply. Then the total impedance being 22.525, angle of minus 6,943 degrees. So this was going to give us the total current divide. Polar form, 11.099, subtract. So that's 0 minus, that will be a plus, 6,943 degrees. So that's our total current in polar form. In a case that you need this to be converted, then we have to convert if in a case that you need this. But in this case, guys, total current, just leave it as it is. All right. Let us consider the other part of our question now, which is to calculate the currents in each branch. So the total current has got no effect to this. We're going to calculate I1, I2 separately. This is now for the currents in each branch. We are still on question 2.11. 2.21. So the current in each branch, that is current in each branch. So considering that there is I1 and I2, this is a parallel circuit. And in a parallel circuit, we do understand that the voltage is the same. The voltage that we have here is the same as the voltage that we have here. So you can take that as an advantage to calculate I1. It is just the supply over Z1, which is our Z coil. In polar form for division, V1 is 250 at an angle of 0 degrees. Then our Z1, we calculated Z coil. In polar form, we have got this. So it is best that you do divide in polar form. So that was going to be 35.630.03. And the angle there is 38,146 degrees. So that's it. You have got your current I1. Divide the numbers separately. This was going to give us 7,022. Then you subtract the angles, minus 38,146. All right. So this is your current in the coil. All right. That is current one, the current that is across the coil. We also need the current I2 that is in this branch. You need I2. So again, it's a parallel combination. The voltage is the same. So that's V over Z2. All right. Having the V250 at an angle of 0 degrees. All right. Then Z2 in polar form division, it's best that we just consider this in polar form. So you are going to consider your Z2 in this case, which is this one. Remember, I talked about this, that there was just an error from our memo, because if you convert this, it was supposed to be 31,637. All right, then that's 45,943 degrees. All right, so that's it. You're going to have I2. So dividing the numbers separately, that was going to give us 7,902. Then you subtract the angles in polar form. If you're dividing, subtract, that's 0 minus, it will be a plus, 45,943 degrees. So that is our current I2. So we managed to calculate the current that is in each branch, the current across the coil, and also the current across the RC circuit. Remember, we had an RC circuit and an RL circuit in this case. All right. Then consider the last part, which is the power and the power factor. The power and the power factor. So when you are considering the power and the power factor, you consider this taken from the total current. All right. So that's from the total current. We want to note what was happening from the total current. What is the relationship between the angle that you are given, the phase angle? Remember, this is your total current here. All right. From this evaluation that we got, this is our total current, which is having 6,943 and so on. So meaning to say we have got the power factor, and from there we can calculate what? We can calculate our power. Remember, power, this is a single phase. This is not a three-phase. So power, you just take your power as it is. Power is equal to VI, the cosine of theta. So the cosine of theta is the power factor. That is your power factor, the cosine of theta. So meaning to say you already have the power factor cos theta. The angle that we are given there, it was 6,943 degrees. That means we have got a power factor of 0,9. If you find this cos 6, that's 0,93. All right, something like that. All right. So this is your power factor. And as you are to consider from this current that you are given, it means that comparing with the voltage, this is leading, it's having a positive. So the current is leading the voltage in this case, all right? Considering the current, it is leading the voltage. All right. So this is leading the voltage, comparing current and what? Current and the voltage. So then you can calculate the power, that is VI cos theta, 250. So they've got 250 times the current. Remember, you need the total current there. Our total current was 11.099 times the cosine of theta, which is 0, this, or just use the cosine of the angle that you're already given, 9.43 as it is. So this was going to give us the power 2,754.402 in watts. So you can even convert this to kilowatts. If you are given this, you can even convert to kilowatts. So these are your typical questions, 20 marks for that. So there you are given everything all in all, which was supposed to be a 20 marks. So as you can see, AC, draw your diagrams, understand your diagram like the one that you're given, then just revise your basics of your electrotechnics and for your industrial electronics and for those basics that you have. This is the one that you're going to be working with. Actually, that's the one that you should simply applying, unless if the question is now of a 3-phase. But for single phase, just revise your N4 as it was. So these are your typical questions that you might be given. As you can see, 20 marks on everything. So more questions of this till we meet again.